Hello and welcome to today's Tech Talk. My name is Bilal Shah and I'm part of AutoPIPE's development team. Today we will be talking about flange analysis using AutoPIPE to minimize the risk of flange failure resulting in a leakage flange. So covering today's topics, we would go through an overview of the root causes of flange failures, the risk associated with flange leak, and we have a quick discussion on an approach that we can take uh, in a workflow for suitable and suggested workflow for methods that needs to be used for the flange analysis and when to use that. And finally, we will have a quick overview on how you can perform flange design in AutoPIPE and also how you can be able to customize your input data to meet your requirements. So let's get started with an overview of flange leakages in general. If you look up the definition of a flange in a dictionary, it will probably tell you something like a flange is an external or internal ridge or rim for attachment to another object as flange on the end of a pipe steam cylinder. So basically, the word flange is coming out from the basic shape that the flange has and its objective of being able to connect to some other object. So basically, bolted flange system is a method to connect piping system, vessels, heat exchangers, valves, and equipments together for a piping system to be complete and pressurized. The advantage of bolted flange is that it provides access for cleaning, inspection, and maintenance of piping systems. When required, a flange joint has two flanges with a gasket in between them for sealing and tightening the bolt. So seemingly this is a simple mechanism. And one could argue that what could go wrong? So let's have a look at some of the common causes of flange leakages, the risk associated with a leaking flange, and how to prevent a leaking flange. We can categorize the root causes of flange failure into these three categories. There could be other categories, but for this presentation, let's categorize them into design, installation, and operation failures. There could be errors made during the design of the flange, like improper gasket selection. This could include selecting a gasket material with chemical properties which are not adequate for the fluid that is being sealed, or the pressure or temperature of the system is higher than the gasket can withstand. The gasket selection will also depend on the type of flange that is being designed. Incorrect load calculation can also be one of the factors at the flange design stage, which could lead to a flange leakage. Having the bolt tensile stress too close to the yield strength of the bolt, for example, or an excessive load on the gasket, crushing the gasket, are a couple of examples of load calculation mistakes or excess loads. There can also be a possibility of a design condition which involves external loads being ignored for the flange design, leading to a flange leakage. Excessive load on a flange joint can be another reason. For example, in a project you can have a heat exchanger with certain type of flanges that can be fabricated well in advance before actually knowing the loads from the piping assembly that would be exerted on the flange joint. This can lead to excessive load on the flange joint, causing it to leak. These were some examples on the design end on which some leakages or failures of flange can happen. On the installation or manufacturing of flange joint, we can have several root causes for flange leakage. The installation process is probably the category to which many flange failures can be attributed, which includes excess bolt loads or insufficient bolt loads or uneven bolt loading onto different bolts around the flange. Then you can have dirt on the surface of the flange or any other debris on the surface of the flange or on the gasket, or you can have a damaged flange face. So on the right side, you can see basically on the left picture that this is a pressure film which actually captures the pressure onto the gasket. In the right over here in the pink color, this is the pressure on the gasket. On the right side, the difference between these two is that one was actually tightened with washers on the studs and the other was without. So you can see that you already have a leakage possibilities in the areas where there is lower pressure, and that could cause a flange leakage. And then on the operation side, you can have excessive thermal gradients, excessive loads again, and gasket reuse during maintenance. If you reuse a gasket, it can lead to a leakage flange, and then you can have excessive vibration, which can also lead to a failed or a leaking gasket. The associated risks from a flange that is leaking. So first and the obvious is the health and safety hazards. There could be a fire or an explosion due to any of the medium escaping out of the flange and causing an explosion. There could be high or low temperature exposures due to the leaking flange to the surrounding environment and to the personals. And then there could be a release of toxic chemicals that are included in the piping system, and they could escape out into the atmosphere. It can also result in additional repair costs for repairing the flanges. It can result in a delayed production, which can cause a lot of financial constraints. And it can also, if there is a new plant that is being constructed and being handed over to the operator, right? The startup may actually get delayed, and some penalties may also be due to that delay. So these are some of the associated risks with actually having a flange failure. So generally preventing the flange leakage, what we could do, one of the most important thing is the tightening protocol, which you have to have tools which can actually apply the torque that is being given in the design specifications. You should be having a protocol. You should be following certain set of rules on how you can actually tighten the bolts, in which series, and how can you actually properly install the gasket, apply even loads, and get away from unbalanced loads, and many of other practical considerations during the tightening or manufacturing of the flange on the site. So ASME PCC1 is a good document which actually deals with some of those protocols as well, and how to document them. The gasket material selection is another way in which you should be careful when selecting the gasket material, so that the medium, it should not be chemically responsive to the medium that is being flowing in the piping system. You can reduce loads on the flanges. Once the piping assembly is connected to the flanges, you can introduce expansion loops. You can introduce flexible joints so that your critical flanges does not experience excessive loads. You can perform design for all conditions. That is something related to design. You can actually take into account the external moments and forces from different sources, from different operating conditions, and other mechanical loads that piping or the flange joint can experience, and all those conditions should be taken into account. And then you have an option of probably going for a detailed FEA analysis using an FEA tool to actually model the whole flange joint assembly into an FEA tool to get more accurate or better results based on the criticality or the location of the flange. So moving on to design basis for some of the available methodologies for flange design. So first of all, we have the standard flanges, which can be selected by using P16.5 or P16.47, which has the pressure temperature rating tables available in them for B16.5 and B16.47, you can select the flange material, you can select operating temperature, and then you can actually get a working pressure values can be obtained from these tables, which would actually let you select a standard flange. And then probably most of you have already uh, done that procedure in your experience. Another flange design method is the Kellogg equivalent pressure method. The Kellogg equivalent pressure method is account for external axial loads, external applied moments, which the B16.5 or the standard flanges selection method could not really take into consideration. So it calculates the effective pressure value or the equivalent pressure value and then adds it to the design or operating pressure to give you an effective flange pressure. Then you can use that effective flange pressure for your selection of your ANSI flange using the temperature pressure tables as were shown in the previous slide. So this is a conservative approach. It would give you higher results for your equivalent pressure, and that could actually lead to a more higher class flange than is actually required. So over here you can see the equation. So M is the external bending moment that the flange experience, and F is the external axial force, which is tension only. Compression is not taken into consideration. And G is the diameter at the location of gasket load reaction. So the location at which your gasket is placed on the flange, that is the diameter of that location from the center of the flange. And then the effective flange pressure is calculated by adding the operating pressure with this equivalent pressure and then going on to select a flange from the temperature pressure tables of B16.5 and B16.47. The basis for Taylor-Forge method. So the ASME flange design methods are generally based on the Taylor-Forge method, and this goes ways back into in the 40s and 50s, in which they actually came up with the initial design basis for the Taylor-Forge method. So the basic idea here is load balancing. So for ASME flange design or the Taylor-Forge method, two different bolt loads are calculated separately for two different conditions. First, the load at the bolting up or gasket seating condition over here, and then the second stress or the load for the bolt is calculated for the operating conditions. So ASME flange design also provides criteria for longitudinal hub stress, radial flange stress, tangential flange stress, and also allows for taking into account external pressure, forces, and moments. And there is also a check for the flange rigidity in the ASME flange check introduced into the newer versions of ASME div flange design. There are other methods like the newer EN1591 method available, which employ the more complex model for the bolted flange and takes into account the deformation balance along with the force balance. And of course, a full finite element analysis for a single flange can also be employed. So if you look at this diagram, the bolts would experience, if you start bolting it up, the gasket would start to experience a force that would be equal to what the bolts actually exert in the other direction, right? This is for the gasket seating condition, and these loads would need to be balanced out for the gasket seating condition. And once you are in operation, there would be an additional hydrostatic force as well, which would try to pull apart the flange, and then you need to actually have enough bolt loads on the bolts so that your gasket remains in its position and keeps on sealing the flange joint. So moving on to design methodologies that are available in AutoPIPE, we would have a quick look. So in AutoPIPE, we have the following design methods that are available. We have the ANSI check, the equivalent pressure method, which we discussed in the previous slides. We have ASME section 8 div 1, ASME section 8 div 2, and ASME section 3 appendix 11 methods available. So the ANSI flange loading check essentially involves determining the effective pressure as we have mentioned earlier, and then we can actually compare it with the allowable pressure in the table 2 of ASME P16.5 and 16.47. So AutoPIPE internally checks these pressure values, equivalent pressure values for all the external loads that's been exerted by the flange, and the effective pressure. If the effective pressure is greater than the allowable pressure, then the flange is operating beyond its rated capacity, and so AutoPIPE would suggest to select the next ratings flange for that ANSI check or for that flange location in the report. The ASME section 8 div 1 and div 2 method calculates all the stresses that we discussed in the previous slide: the tangential stress, the longitudinal hub stress, and the rigidity as well. There are the main difference between ASME section 8 div 1 and div 2 flanges analysis method is that division 1 refers to allowable stresses listed in table 1A and 1B from ASME section 2 part D, and division 2 refers to allowable stresses listed in table 5A and 5B. So that's one of the main difference, and another difference is the consideration of additional external moment due to the axial force and bending moment applied to the flange. This is only included in division 2 flange analysis method. However, in AutoPIPE, we have made this an option for consideration in the division 1 flange analysis method as well. So these were the basic two differences between div 1 and div 2, and as we go on to appendix 11 method, so it is again nearly identical to those described in division 1, with some of the flanges not being available, like no single or double split ring configuration is available, there are no reverse type flanges, and there is no rigidity criteria being considered. So these are some of the differences between div 1, div 2, and appendix 11. And obviously ANSI check, which is using the equivalent pressure method, is altogether different from both of these three methods, and is much more conservative. So let's move on to have a general workflow, or which method to use and when to use that. So a general workflow, suggested workflow could be that you can perform an initial pass using ANSI flange check, and then see which of the flanges are failing that conservative method, right? And if you see some of the flanges failing, right, you can perform a secondary pass for flanges that fail, or on the boundary condition for ANSI flange check. That could be one way of going about it. There are also some special considerations that would require maybe more than the ANSI flange check or Taylor forge method. So one of them could be thermal shocks if you have a location which you can have large thermal gradients, or if you have a flange, a heavy bodied flange, which has a huge thermal mass, and the edges or the outer ends of the flange would experience a lower temperature than the inner body of the flange, which is in contact with the medium that is passing through them. It can actually lead to thermal shock or thermal gradients, which would require some more considerations. And then if there's a fatigue, if fatigue is a concern, that's another area in which you can actually look towards having some special consideration or want to have maybe go for a full FEA analysis. And flanges that are not covered by ASME, or if there are some specialized flanges, then that is also a scenario in which you could actually think about going for a full FEA analysis instead of using the Taylor force or the equivalent pressure method that are available. There could also be you can assess the criticality of the location. So if there are critical joints which can result in loss in production, hazardous material releases, or any other location which is critical to the operation of the plant, you can then also consider further FE analysis along with actually using the Taylor force method or the ASME div 1, div 2 or appendix 11 method along with the ANSI flange check or maybe even further FE analysis. So moving on to design and customization inside AutoPIPE for and how to perform them. So we would first go through the flange, the user interface of the flange dialog that is available, which is a model dialog, and we would see how it is integrated into the program. The input data, we would go through that quickly, the analysis and the reports. And then we can actually have an example of how you can actually customize the data for the input data or the geometrical or material data and into the libraries so that you can use your custom materials or custom flange materials, gaskets or anything else. So I already have the class 1 tutorial example model opened in front of you. If you guys can already see that, I would try to move slowly the screen so that you guys should actually follow at which point I am and then which screen I'm talking about. So we have only a single flange in this model at B30. So we would first perform an analysis of the model so that results are available for this model, which would then be used by the flange analysis to perform the flange design. So once the analysis is done, right, we can go on to the flange analysis dialog. This is integrated as well as, you know, it is something which is a model window, which means that you can actually continue to work with the model once this dialog is open. It's not going to block your access to the model, and it's also bidirectional. If you select on the grid, if you select this flange, it would actually highlight the flange over there and vice versa as well. If you can select the flange in the model, it's going to get highlighted here. So that's a nice thing to have. And then you can double click onto any of the grid entry, and then you can actually see the flange dialog popping up right from the flange analysis dialog, and you don't need to actually go back to the model or anything to change any of the properties over here. So the user interface for the flange analysis dialog, we have many different tabs. We have the analysis tab as the first tab. We have load, flange, pipe, bolts, and gasket. So the names are self-explanatory. The loads would deal with defining the load. The flange would deal with selection of the gasket, the flange material and dimensions. And we would go through the rest of tabs once we actually go into design of an ASME div 1 flange. So you have some further options here. The option of hide duplicate flanges is there. So there are two flanges in the model connected at the same point. I can select hide duplicate flanges and one of them would go away. So that leaves me with just a single entry. That is something you could do. You can also select highlight incomplete flanges. which would actually tell you and highlight if there are any incomplete flanges in the model or in this flange analysis dialog, and it will highlight all the tabs which is incomplete data. So the analysis methods, as we saw earlier, we have the ANSI check, we have the ASME section 8 div 1, div 2, and ASME section 3 appendix 11. So first off, as we discussed, we can go through the ANSI check. Before going there, you already have these check boxes for showing the sketch and showing the tag of the flange as well. So if you check the show sketch, it's going to show you a small sketch of the flange that is being currently selected. So checking on the analysis for the ANSI check. So the ANSI check is simple enough. It doesn't require much data. So all the tabs with the steric on top of it, these are the inputs that are required for ASME analysis method, ASME div 1 div 2 analysis method. For ANSI check, you probably need only the analysis tab to select which analysis, and then you can actually select a material from here, your flange material, and you can actually enter some user pressure values if you want to. Otherwise, the program is going to pick it automatically from the selected loads which is going to analyze, and then you can select the gasket material for the dimensions of the gasket from B16.5, or if you want to enter your own data, you can always do that by unchecking that and entering your own data. And that would be all that you would require for the ANSI flange check. You can press the analyze. It's going to tell you that there is one flange in this model and that's been analyzed, and we can see that the max ratio is 2.034 and is telling you that this is failed. So let's have a quick look at the report for this flange. We can see that AutoPIPE has automatically calculated the pressure and the allowed pressure and the pressure ratio for all of the non-code combinations that are available for this model by default. And we can see that GT2 is the one which is actually failing. Thermal 2 is also failing the pressure ratio criterion, and it is suggesting us to upgrade it to class 600 or class 900 flange as per the ANSI flange check. So with our first pass failing, right, we can actually go for a more the Taylor Forge analysis method or the division 1-2 method for the flange design. We can select that. As soon as you do that, right, so there are the tabs get highlighted for which there is additional data required. So we will go one by one into the tabs and then see what data is missing and what data you would need to enter for the performance of this flange design. So you have the load combination which you can select. These are all your non-code combinations that are available here. Let's select maximum force and maximum movement from among all the combinations. The operating cases, we would set it to maximum P and maximum thermal case, so it would show the operating temperature, the operating pressure, and if you want to enter any external pressure that you want to get incorporated into the calculations for the flange stresses, you can enter that here. And it's also telling you the bending moment and the applied combination from which that bending moment is coming from. So we have selected the load combination as the max force, max moment, and it is telling us that gravity is actually resulting in the maximum axial force, and applied bending moment is coming from thermal 2 non-code combination. Moving on to the flange, you can select the attachment as either integral or loose or an optional. And these are the three basic types which are provided by ASME div 1 and div 2, in which it would say if this is a ring type flange attached with weld, it would say it's loose, or if it's an integral flange, it would consider it as an integral, and the calculations would differ based on what selection is being made here. For the flange material, you can either press the select button or you can just simply uh, uh, look at the drop down. So the pipe material, if I can recall, for this pipe was SA335. So I would want to select the similar pipe flange material, and flange bore dimensions are coming in from B16.5, and then there is a rigidity factor required for the rigidity criterion, and rest of all the data is automatically picked up by the program once a selection is made for the flange bore dimensions. Then going on to the pipe material is SA335 P22 with its allowable stress and allowable stress at operating and ambient temperature. Then we can actually select the bolt material. There are different bolt materials available and thread types, and all rest of the data is automatically populated from the database. And then there is the gasket material that you can select. You can select mineral fiber, you can select spiral wound corrugated uh, gaskets. For this one, we will select the corrugated monochrome and mineral fiber fill. So let's go to analyzing this more this flange. And as soon as the analysis is performed really quickly, and we can see the max ratio given by this report, or for the ASME section 8 div 1 is 0.899. So as the ANSI flange check is basically a bit more conservative, right? We can see that maybe using the correct data in the ASME section 8 div 1, the flange is actually passing all the checks, and this max ratio is from among all the bolt loads required, or longitudinal hub stress or radial stresses. So let's have a quick look at the report as well. The report is going to echo the inputs, all the inputs that are being entered for the flange, the pipe inputs, the gasket inputs, uh, the bolt inputs, the pressure and temperature loads that are being applied, a summary of which design code is being used, and a bit of a data about the flange volume, flange diameter. Then the allowable stresses values for operating conditions and the gasket seating condition. They are actually calculated, and then the tangential flange stress, ST, radial flange stress, longitudinal hub stress, all these values are calculated both for the seating, gasket seating condition and operating condition. And then the rigidity criteria is also provided, and then you can see that the rigidity criteria is also passing for this flange, and the ratio should be less than 1.0, with G as the rigidity index for both the operating and gasket seating condition. Then the stress factors that are being used or calculated during these calculations are displayed, and along with a summary of what are the forces and what are the moment arm, and how these stresses are derived at, what are the actual moments acting on for the calculation of the operating conditions, including all the external moments as well. And then there are any warnings or errors. There are no errors. There is one warning, and there could be other warnings as well that we could see. So that was a real quick rundown of flange design, and probably how you can perform that in AutoPIPE. I will really quickly jump on to the customization. If you want, we have the flange database available in along with the AutoPIPE installation. So that goes into the program data, Bentley, and then the version of the program that you're using, and it's labeled as ASME2010.mdb. And there you can actually see all these tables. for example, if I wanted to maybe say add uh, another material, a flange material, right, which is not available by default in these libraries, right, what I can probably do is I can uh, go to the very end, right, enter a new record for saving time, right. So I've already entered uh, a new uh, flange material with copying the data from the previous record. You can actually change that by looking at what material it is, what is the product type, what is the is it section, is it plates, is it forging, what is the material spec, and then giving the values uh, at different temperature, like at 20, 100, and 150, and you can change these values. Like I can set this to say 22 and save this to 20, and let's just save this database, right, and close this down and go back to AutoPIPE, close this flange analysis dialog. I'm going to reload this again and go to the flange, go to select material. It's going to take a bit of a time to load up all the materials. So I selected, I think it was plates, right? And it was copper, and nope, it wasn't plates. So at the end, I can see an SP Tech Talk material already added with the properties that I defined in that. Like you can see the 22.0 stress at 20 degrees centigrade, which I just entered. So that's how you can customize the input data as well if you want to. And that's pretty much all I wanted to talk about today. Before leaving, uh, let me see if I can go to the correct slide. So we went through the customization, right? And now I'll leave you with some documents that you can look through or go through for further discussions, and some documents like ASME PCC1. This is a good document with guidelines for pressure boundary bolted flange joint assembly. It contains a lot of practical advice, on how to actually come up with a bolting technique, what bolting patterns to use, and so many other details on flanges. Then the ASME BPVC Section 8, Div 1, Appendix 2, Appendix Y, and Appendix S. These are all the appendices which deals with the practical consideration and design considerations of flanges. Then we move on to Div 2, Article 4.16, which is designed for rules for flange joints, and Appendix 11, which we've discussed during the Tech Talk as well. One of the methods that is available in AutoPIPE with rules for ported flange connection for class 2 and 3. There is a good document on modern flange design. It was named modern way back in I think 50s and 60s. At that time, they thought that was the modern flange design. You can give a search on Google, and it's going to give you the basic design basis as well as the calculations and the evolution that flange design has gone through. And then there's a book on evaluation of bolting and flanges for SPP 16.5, also a very good reference for flange design. And there's a nice 8 to 10 pages paper on risk analysis for the prevention of leaking flanges in process plants by Jutta. That's also something that you can find interesting. So I thank you for your time, and I hope you enjoyed today's Tech Talk, and we can now move on to the questions.
Okay, Bilal, we have a couple of questions, starting with the first one here. How do I enter a pressure value different than the operating pressure cases to be considered for the ANSI check?
Okay, Uh, do I have sharing? Uh, Right. So even if I don't have the sharing, what you can do is for the ANSI check, right? You can actually select or enter on the ANSI check. There is a button for entering using Pmax at the bottom. You can use that to enter your pressure values or user pressure values into the program, which would then actually be used for the ANSI flange check. Otherwise, the ANSI flange check would actually pick up the associated pressure values from the non-thermal or non-code combination which is being used. Um, when calculating bolt tensile stress for operating condition, it seems AutoPIPE is not taking external loads into account. All right. Uh, I think this could be, if it is, this could potentially be a problem with the program if you know it's supposed to actually take into account the external loads. The ASME div 1 div 2 actually gives these calculations on how the external movements can be calculated, and MO operating is calculated based off on the external movement being included into the calculations. If you have a specific example, I think we can definitely discuss that further, or we can look at it. The external movements should be a part of that. Can you restart where the ANSI checks are coming from? Is this just B16.5? So okay, so is this just the B16.5 tables? So basically, the ANSI check is coming from, if we go through the presentation, right? This is basically known as the ANSI. The basis for the ANSI flange check is the Kellogg equivalent pressure method, right? This is coming in from the equation for equivalent pressure method calculation. So the only thing that AutoPIPE has done is that it uses the equivalent pressure equation and calculates that equivalent pressure, adds it to the operating pressure, gets an effective flange pressure, and then use that effective flange pressure for the selection of a flange from ANSI tables. So that is how it is incorporated inside AutoPIPE. So the method itself, you know, employs the Kellogg's equivalent pressure method.
Okay, we have another question. Does AutoPIPE report the required bolt loads?
Right. AutoPIPE does report the required bolt loads into the reports. If you look out onto the output report, you can actually see the gasket seating condition as well as the operational condition, and the bolt loads would be displayed there.
Okay, and a final question here. Does AutoPIPE flange analysis deal with the flange rigidity for leakage?
Yes, as mentioned during the presentation as well, the ANSI check does not, obviously, but the division 1 uh, does actually take into consideration the flange rigidity, and that's why you need to actually enter the rigidity factor in the input, and rigidity stress or rigidity factor along with the allowable of 1, which is always 1, is a unity check. So it's that would be displayed in the reports as well. And the check itself, you know, what you see on the analysis tab is sort of like the maximum of all these stress ratios which you can actually get. So there's another question. Small diameter flanges with spiral wound gasket have leakage in seating conditions. Is it not recommended to use spiral wound gasket then for such condition? That would be some sort of like a practical consideration. which probably the question is probably more aware of. From the standpoint of how the design is carried out, it actually takes the maximum from the operating and the gasket seating condition. So whichever is greater, that is what the code recommends to use the loads or the board loads or the stresses, whichever is maximum from the gasket seating condition and from the operating condition.